Welcome again. Today we will discuss copper based reagents in organic synthesis. As you know, copper is very cheap metal, so it has been used in many organic transformations. So first one we will discuss Gilman reagent, and then we will discuss reactions of Gilman reagent: conjugate addition, tandem 1,4 addition, enolate coupling, reactions with acyl chlorides, that is also very important reaction, reaction with aldehyde and ketones 1,2 fashion, reaction with epoxides, higher order mixed cuprates, they are much useful, we will see, and copper catalyzed allylic substitution, and here generally hard nucleophile reacts. So this is special also, hard nucleophiles react with copper catalysis allylic reaction, and Cadiot-Chodkiewicz coupling we will see, Glaser oxidative coupling, Ullmann reaction for biaryl synthesis, Goldman reaction amine synthesis, and Castro-Stephan coupling for alkyne synthesis we will see. So first we will discuss some characteristics of organocopper compounds. So copper is less electropositive than lithium and magnesium, so C-Cu bond is less polarized than the C-lithium and C-magnesium bonds. This difference produces three useful changes in reactivity. Like organocopper reagents react with alkyl, alkynyl and aryl halides to give alkylated products. So this is very important. Unlike lithium and magnesium, they give the coupling reaction with alkyl, alkynyl and aryl halides. Organocopper reagents more selective and can be acylated with acid chlorides without concomitant attack on ketones, alkyl halides and esters. So the relative reactivity is the RCOCl is higher than aldehyde. So it is possible to react with acid chloride in presence of aldehyde. Then tosylates, iodides, epoxides, bromides, ketones, esters, nitriles. Also in reactions with alpha beta unsaturated carbonyl compounds, the organocopper reagents prefer 1,4 addition over 1,2 addition, and that is its major use in organic synthesis, the 1,4 addition compared to 1,2 addition, because we know that Gignard give 1,2 addition, and for 1,4 addition you have to use the cuprates. So now we will see just an overview of different reactions. The nucleophilic organocopper 1 reagents are commonly described as simple organocopper species RCU or R2CU, or metal organocuprates such as R2CuM homocuprate and RCUX, where X is cyano or halide heterocuprate, where Rx and M stand for a carbanion, as for example alkyl, alkynyl, aryl, a non-transferable anion, as for example halide, heteroatom anion, cyanide, and a main group metal cation, as for example lithium plus, magnesium 2 plus, zinc 2 plus respectively. So this is the reagent RCU, this is R2CU Li and RCUX Li, this is heterocuprate, and this is RMGXCUY. So this you can generate from the Gignard reagent. So this reagent can react with alkyne to generate this vinyl cuprate. Also it can do substitution reaction with alkyl halide to give this product. Also it can react with epoxide to generate an alkoxide, which after aqueous workup will give you the alcohol, and with allylic acetate or halide, this kind of allylic substitution is possible. So here this is alpha substitution, this is gamma substitution, we will see the selectivity. Also in vinyl halide it can give this coupling product, and here the olefin geometry does not change, so we will see. Also this is the useful reaction with acid chloride, you can get the ketone, and this ketone does not further react with cuprate. So this is very important. Then the conjugate addition to E9 system with the carbonyl compound, you get this kind of allyne system. After the addition of R, this triple bond becomes like this, and with an alkynyl ketone also you can get this addition like this to get this product, and here also you can get this is the alpha beta unsaturated ketone, that is the conjugate addition. So, all these three cases conjugate addition is happening. So, this is the major use. Now, we will discuss Gilman reagent. So, Gilman reagent is a homocuprate reagent, that is R2CuLi or R2CuMgX, and a Gilman reagent is a lithium, magnesium and copper diorganocopper reagent compound R2CuLi or R2CuMgX, where R is an alkyl or aryl. These reagents were discovered by Henry Gilman and co-workers, that is why it is called Gilman reagent. Lithium dimethyl copper CH3 can be prepared by adding copper 1 iodide to methyl lithium or Grignard in ether tetrahydrofuran at -78 degrees centigrade. And the initially formed RCON are polymeric and insoluble in ether and THA, but dissolve on addition of a second equivalent of RLI or RMgX. So, this is the reaction for the preparation. So, preparation RM, that can be RLI or MgX, then copper 1 bromide or iodide in ether THF, you get this polymer, and further addition of RM. So, RM should be excess, this should be excess, RM will add to generate this R2CuM. So, this is polymeric and insoluble, that is why you have to make this R2 species, so that it is insoluble. And here is an example of tandem reaction, like here you can see the alkynyl ester is there and here simple ester. So, first it does a conjugate addition. If you add dimethyl cuprate, then it adds to conjugate fashion here. So, this can be mechanism that CH3 minus is reacting here, going to here, and then a substitution kind of reaction is happening, and you get this cyclopentenone in 45%. So, this is an useful reaction that with cuprate you can generate this cyclopentenone in one pot. And there is a book, Modern Organocopper Chemistry, Will Visage 2002. Now, we will see some reactions of this Gilman reagent. So, first is the conjugate addition. Organometallic reagents may add in 1,2 or 1,4 manner to alpha beta unsaturated carbonyl compounds. And here you can see the regioselectivity in addition of RLI, RMgX and organocopper reagents to alpha beta unsaturated carbonyl compound. So, when RLI is reacted with alpha beta, then you get selectively 1,2 addition. With RMgX also you get 1,2 addition. On the other hand, R2CuLi you get the 1,4, RMgX CuX you get the 1,4. So, this is very important because these two are hard and these two are soft. They are hard nucleophile and this is soft nucleophile. So, 1,4 addition, conjugate addition is most successful with soft, relatively non-basic nucleophiles such as cyano, RNH2, RNH, RSH, enoles derived from beta dicarbonyl compounds and organocuprates. So, this is very important. The soft nucleophiles react in the 1,4 fashion, that is the conjugate addition. And 1,2 addition is most successful with hard, relatively basic nucleophiles such as hydride, organolithiums and Grignard. So, this is the 1,2 addition. The nucleophile, it is hard, and we know this carbonyl center also is hard. Then the hard nucleophile reacts in hard nucleophile. So, you get the 1,2 addition. On the other hand, this is the soft. So, this soft nucleophile then adds in the 1,4 fashion and you get the enolate anion, which after aqueous acidic workup you can get the ketone, that is conjugated addition product. Now, we will see example like if you add cyclohexanone with dimethyl cuprate, and after that acidic workup you get this 3-methyl cyclohexanone. On the other hand, if you react with methyl magnesium bromide, then you get this allylic alcohol. So that means 1 to fashion here the reaction happens, and here the 1,4 fashion the reaction happen. This is because Me2CuLi, this is delta plus and delta minus on CH3 minus. Electron pair is shared between carbon and copper atoms over a slight partial charge on carbon atom. So this is soft nucleophile. On the other hand, electron pair negative charge is held close to the carbon atom in case of methyl magnesium bromide, and that's why it is hard nucleophile. So here the alpha beta unsaturated ketone, the LUMO, the beta carbon has the largest coefficient. So the reaction will happen here. Soft species carries a low partial charge, soft nucleophiles react at the alkene. On the other hand, high partial charge on carbon atom of carbonyl, here high plus charge, this is hard electrophile, and that's why hard nucleophiles reacts fastest with hard electrophiles. And hard species carries a charge on or a high partial charge or a high partial charge. So they will react fast, the hard nucleophile, and soft nucleophile will react slowly. Conjugate addition, we will see some example now. In bicyclic system, addition is chemoselective. The reaction occurs at less hindered double bond of the dienone and stereoselective. In that, introduction of methyl group occurs preferentially from less hindered side of the molecule. So this is very important. The reaction will take place from the less hindered side of the substrate. Like here, if you see this substrate, here there is a methyl group which is in the top side. So the attack will take place from the down side. So this is down face attack. And you can see this olefin is trisubstituted, on the other hand this is disubstituted. So this is trisubstituted, this is disubstituted. So this is stereo and regioselective addition. So methyl selectively adds to this double bond and also from the down phase, and after aqueous workup you get this enone in 91% yield. Conjugate addition of lithocuprase to alpha beta unsaturated ketones and ester may proceed via initial reversible copper 1 olefin lithium association, which then undergoes oxidative addition followed by reductive elimination. So the mechanism will be like this. First the coordination happens like this, and copper carries a negative charge here. So lithium coordinates with the carbonyl group, and now the oxidative addition will happen. So oxidative addition here, copper is adding to this carbon and you get this, and now reductive elimination will happen. That is, the methyl will add and copper will eliminate. So you get this copper methyl here, and you get this enolate. Of course, after aqueous workup you will get the carbonyl compound. Addition of Me3SiCl accelerates the conjugate addition of copper reagents to sterically hindered enodes, probably by activating the carbonyl group. So in the case of sterically hindered enodes, the conjugate addition will be slow. In this case, trimethyl silyl chloride will help. In the presence of trimethyl silyl chloride, the enolate initially formed is tapped to give the beta-beta disubstituted silyl enol ether in 99%, then hydrolysis of the silyl enol ether regenerates the carbonyl group. So we will see example like here, this is 3 substituted cyclohexanone. So this is trisubstituted. Earlier we have seen that in trisubstituted cases the dimethyl cuprate did not add, but here if you add this trimethyl silyl chloride and this is the cuprate, then the addition will take place at minus 70 degrees centigrade. You see, this is the quaternary center formed, and you get this product in 99% yield, this enol silane, and this enol silane on acidic workup it give this beta-beta disubstituted ketone. So, this ketone is formed in 99% yield. Reaction of beta-beta disubstituted enones with organocuprates are often not very successful because of steric of the carbon-carbon double bond. In this case, use of R2CI like BF3. So, BF3 etherate is another alternative, often obviates the problem. Possibly, Lewis acid BF3 further polarizes and activates the ketone by coordination. So, in this case also, this is beta-beta disubstituted enone, beta-beta disubstituted enone, and so that is the trisubstituted. So, here also if you add BF3 etherate, then the reaction will happen with this butyl cuprate, the butyl group will add, and after aqueous workup you get this ketone. So, this product also is high yield. Some more examples: Gigner reagents in the presence of CuX or a mixture of MnCl2 and CuI undergo 1,4 addition to hinder enone. So, we have seen the TMS chloride, then we have seen BF3 etherate, manganese chloride. Manganese chloride also can help in this conjugate addition. So, here this is the sterically hindered enones, here also beta-beta disubstituted, and with 30% manganese chloride. Manganese chloride, and this magnesium bromide with 3% copper iodide. So, this will be the Gigner reagent formation in situ, and then THF 0 degree centigrade you get the conjugate addition, that is the N-butyl group is adding, and you get 94% yield of this product. Reaction of dialkyl cuprates with alpha beta unsaturated aldehydes results in the preferential 1,2 addition to the carbonyl group. However, in the presence of Me3SiCl, conjugate addition prevails to furnish after hydrolysis of the resultant cenyl enone ether the saturated aldehyde. So, in the case of alpha beta unsaturated aldehyde, what happens if you add the cuprate, then the 1,2 addition takes place. But if you add in presence of TMS chloride, then the 1,4 addition will take place. We will see an example like here. If you react this alpha beta unsaturated aldehyde with this cuprate in presence of TMS chloride, THM minus 78 degree centigrade, so the conjugate addition will take place. You see the butyl group added, and this enol silane formed 95% yield with greater than 95% E selectivity, and after acidic workup you get the aldehyde. So, if you do an retrosynthesis, that means here you have to generate a plus, here minus. So, plus means the olefin, and you get this product in 80% yield. Some more examples: conjugate addition of dialkyl cuprates to beta substituted alpha beta unsaturated acids and esters give low yield. Addition of boron trifluoride etherate we have already seen to certain dialkyl cuprates, and higher order cuprates enhance their reactivity in Michael addition to conjugated acids and esters. So, this is an example of beta-beta disubstituted alpha beta unsaturated ester. So, this means this center is trisubstituted. So, with N-butyl cuprate you get less than 1% yield. On the other hand, if you add BF3, that is the N-butyl cuprate BF3, then you get the conjugate addition 52% yield of this product. Now, enantioselective variants also is possible. Diastereoselective conjugate addition reactions of chiral organocuprates provide beta functionalized ketones in high yield and diastereoselectivity. A disadvantage of course of this reaction is the requirement of a full equivalent of enantiopure starting material. So, in this case you have to use enantiopure starting material 1 equivalent. So, the cuprate itself is chiral. So, the cuprate is chiral here, and this cuprate you can see there is a chiral center here, and if you add to cyclohexenone, then the conjugate addition will take place selectively. So, here a chiral center is forming, newly generated, and this product will be formed in 87% yield and greater than 97% diastereomeric excess. So, this is very important, the selectivity is very good, diastomeric excess DE means. However, one drawback of this method, that stoichiometric amount of the chiral starting material you have to use, and this was published in Tetragon Letters 1982. So, that is why the catalytic version, catalytic enantioselective methods have been developed based on the copper 1 catalyzed conjugate addition of Gigner reactions to enones. The proposed mechanism involves transmetallation from the Gigner reagent to copper, conjugate addition and redetermining reductive elimination. So, this kind of mechanism we have seen earlier, that the copper will first the oxidative addition will happen and then the reductive elimination. Like here, this is the alpha beta unsaturated A star or thioester, and the Gigner is present now copper 1 mole percent, L1 or L2. So, these are the structure of the L1. L1 is RS Josephus, here triphenyl phosphine is there, and here cyclohexyl phosphine, and here just change happened, this become now PPH2 and this is the PCY2. So, here this was PPH2, PCY2. Now, with this ligand 1.1 mole percent only, minus 78 degree centigrade tert-butyl methyl ether, you get this conjugated addition product up to 99%. So, this is very important. With catalytic amount, catalytic phosphine catalyst, you can get high enantioselectivity. So, we will discuss the mechanism, what is happening here. Now, first the ligand, that is the phosphine ligand, binds with the copper. So, this is very important. You see, these are the phosphine PP and it is binding with the copper. So, this is chiral and dimeric species is forming, that is going to monomer like this, and in the monomer it can react with Gignard, and after Gignard it is forming the complex A, this kind of complex where R is binding with copper. So, this is very important, R is binding with copper and copper is binding with chiral ligand. So, what will happen? R is in the chiral environment, and now if it is adding to the alpha beta unsaturated A star or ketone reaction intermediate. So, this will give the intermediate, that the conjugate addition is happening here, conjugate addition, and the conjugate addition in chiral fashion. So, this chiral center will be determined, and after that this will be reductively eliminate this copper species monomeric, and after aqueous workup you get the ester or ketone. So, this is very important, the catalytic amount of phosphine and copper can give you the product in high enantiomeric ratio. This was published in JACS 2006 1 to 8. This is the issue and this is the page number 9103. Now, we will discuss tandem 1,4 addition. So, so far we have seen the only one bond formation, now we can see two bond formation. So, here after the addition you can see the enolate is forming. So, this is an enolate actually, and that enolate you can trap, that enolate you can trap either that the oxygen center O trapping, that is called, and electrophile can be R3SiCl, that we have already seen, and phosphorus chloride also you can use. On the other hand, C trapping can be done by, if you treat with alkyl halide, aldehyde, even halogens, that will give the C trapping. So, O trapping will give you this product, enol product. On the other hand, C trapping will give you this alpha beta. This is very important, alpha beta disubstitution. Disubstitution, and generally this product is trans when the C trapping happens. Enolate generated from enone below reacts at oxygen with chlorotrimethylsilane in the presence of triethylamine to produce the trimethylsilyl enol ether. Silyl enol ethers are variable intermediates to the preparation of regio-defined enolates. Like here, you see, this was a this is a chiral center actually, and when it adding with this cuprate, and if you coincidence with trimethylsilyl chloride, triethylamine, HMPA, then this enolate is forming. This is the silyl enolate, and you can see this chiral center, this is opposite to this methyl. So, these are trans, and this product is forming in 86% yield. Some more examples of O trapping. Now, treatment of enolates with this RO whole to POCl also results in O trapping to yield the corresponding enol phosphates. So, earlier we have seen enol silane, now we will see enol phosphates. Dissolving metal reduction of enol phosphates is useful for the deoxygenation of ketones with concomitant regiospecific formation of the alkene. So, here this is two chiral centers are present. Now, the control will be done by this chiral. So, this will be down and this is up. So, after two steps you get this enol phosphate, and this enol phosphates, one usefulness of enol phosphates, that earlier we have seen the enol silane, the aqueous workup generate the ketone, but enol phosphate you can generate the olefin. So, this is very important. Just you have to treat with lithium, ethylamine and tertiary butanol solvent, you get this olefin in 99% yield. So, this is very important. This is like deoxygenation reaction. Deoxygenation reaction most likely going by radical mechanism. So far we have seen the O trapping, now we will see C trapping. So, alkylation or hydroxyalkylation, that is the hydroxyalkylation if you react with aldehyde of enolates derived from conjugate addition of organocuprates affords vicinal dialkylated products. So, this is very important, alpha beta disubstitution, like here N-butyl cuprate, first the conjugate addition and then the C trapping with iodomethane, you get this methyl group and they are in the trans. So, this is the major isomer, this is the workup. Enolates obtained from conjugate addition of homocuprates or copper catalyzed Gigner reagents undergo aldol condensation with aldehydes in the presence of zinc chloride to give stereoisomeric mixture of aldol product. So, if you put zinc chloride, then this, so first this R2CuLi and then R-CHO, and here if you add the zinc, then what will happen? Suppose this will be from down and this will be up. So, you get the OH R1. So, this is the hydroxymethylation, this product you can get. Now, we will discuss reaction with acid chloride. So far we have discussed the conjugate addition, now we will see the reaction with carbonyl group. First we will discuss reaction with acid chloride. The reaction of dialkyl cuprate and acid chloride is a preferred method to synthesize ketones. Unlike in the case of Gigner reagents, the ketones formed do not react with organocopper reagent. Like here, it is an acid chloride, and you can see there is a ester motif also. Now, if you react with this cuprate, what happens? The acid chloride is only reacting and you get this ketone. So, this is very important, the ester is not reacting. This ketone is forming, also this ketone is stable. So, ketone does not further react, that earlier I have told that ketone does not further react. So, it is very important method then for the preparation of ketones. Like here 4-nitrobenzoyl chloride, if you treat with dimethyl cuprate, then you can get this 4-nitroacetophenone. Also, if you see this complex structure, here a acid chloride motif is there, here a ketal motif is present, and here a thioester motif is present, and with diethyl cuprate minus 78 degrees centigrade, only this acid chloride reacted and you get this ketone. So, selectively acid chloride is reacting. Now, we will discuss reaction with aldehyde and ketones. We have told the reaction of acid chloride will be faster than aldehyde and ketones, but the reaction is possible. Organocuprates react with aldehydes to give alcohols in high yield. In the presence of chlorotrimethyl the corresponding O-silyl ethers can be obtained. Like here, if you react dimethyl cuprate with this aldehyde, as you can see there is ether is there and minus 78 degree centigrade, then this 1,2 addition product you can get, 1,2 addition product with aldehyde selectively, and you can get anticene ratio 30:1. Also, if you have this alpha branch aldehyde and N-butyl cuprate, then quenching with trimethyl chloride, where the reaction will be faster, and minus 78 degree centigrade THF, you get these two products, 64:1 ratio, and you can see this phenyl, actually here one carbon is less, so this will not be there, and this butyl group, they will be trans to each other, and here they are cis to each other. So this is cis, this is trans. So trans will be measured 64:1 ratio. The reaction of ketones with organocuprates is very sluggish. So enones will react in 1,4 fashion, but simple ketones the reaction is very sluggish. However, the reaction takes place conveniently in the presence of chlorotrimethylsilane. So this is very important. Simple ketones does not react, but if you put trimethyl chloride, then the reaction will happen, possibly by the activation of the carbonyl group. And here you can get this trans, you see this trans product form as the major product. Reactions with epoxides also is possible. The epoxide is attacked by organocopper reagents at the least substituted carbon atom, giving the corresponding alcohol. Like here, this is the terminal epoxide, and the reaction will take place regioselectively. So regioselectively, this is the major product will form. So Me2Culi attack from the less hindered carbon. Now reactions with vinyl halides, this is very important reaction. The coupling of alkynyl bromides or iodides with organocuprates proceeds with high stereoselectivity. Like here, this vinyl iodide, so you can see this is trans, and the product also is trans. So what happens? The double bond geometry is not changing in this process, and selectively the Ci bond is replaced with this bond. So N-butyl group is coming, just N-butyl cuprate ether minus 95 degree centigrade 1 hour, you get this product 71%. And here also this similar mechanism, the oxidative addition and reductive elimination is occurring to get this substituted olefin. Now we will discuss higher order mixed cuprates Lipschutz reagent. So far the reaction we have discussed with Gilman reagent, now Lipschutz reagent. Cuprates are useful, but there are few problems associated with them. To overcome this limitation, Lipschutz developed higher order mixed cuprates R2CuCnLi2 by the reaction of organolithium reagent with cuprous cyanide. So this is the reaction 2RiL plus CuCN. So here this cyano group will be in the reagent R2CuCnLi2. Higher order cuprates show greater reactivity compared to Gilman reagents with alkyl halides, even secondary halides. For example, S2-bromo-octane reacts with ETMeCuCnLi at 0 degree centigrade to give R3-methyl nonene in 72% yield. So this is very important. Simple Gilman reagents give sluggish reaction with alkyl halides, but the reactivity is increased with this Lipschutz reagent. One example, so this is the 2-bromo-octane, and when it is reacted with this ETMeCuCnLi2, you get an inversion of course. So this is inversion because this is a substitution reaction, but selectively the ethyl group is incorporated into the product and you get high yield also. So that is the usefulness of Lipschutz reagent. Some more example, opening of epoxide ring is more efficient with the higher order cuprate than with Gilman reagents, and attack takes place at the less radically hindered carbon. So this is also important that it is much reactive than the Gilman reagent. Suppose if you have this epoxide, so this is chiral. However, the one side This side it is tetrasubstituted, this side it is trisubstituted. So, what will happen? The reaction will selectively happen this side only. Now, if you add only this cuprate in ether 0 degree centigrade, you get the product that the epoxide opening product is happening like earlier we have seen, but the yield is 30%. On the other hand, if you use the Lipschutz reagent, then the yield is much higher. Here you have to use THF solvent 0 degree centigrade 6 hours, you get 86% yield. The same product is forming, but the yield is much higher. Also, higher order cuprates reacts with unsaturated carbonyl compounds as Gilman reagent to afford the addition product in excellent yield. Like here, if you add this reagent with this substrate, this is complex structure, you can see. Now, this is bicyclic system. Now, the addition will take place selectively from the down phase here and you get 90% yield. So, very high yield. So, conjugate addition case also very high yield for the product you can get. Now, we will see different reaction, that is the copper mediated allylic substitution. Earlier we have seen the palladium catalyzed allylic substitution, now we will see copper catalyzed allylic substitution. And one difference is the palladium catalysis, the soft nucleophiles can be employed, but here hard nucleophiles. So, copper catalyzed allylic substitution is typically conducted with hard non-stabilized carbonucleophiles instead of the soft stabilized carbonucleophiles, used most often in the allylic substitution catalyzed by other transition metals like palladium, iridium system. The most common nucleophiles used in copper catalyzed allylic substitutions are diorganozinc reagents, Gigner reagents, organolithium reagents and trialkyl aluminum reagents. So, these are hard nucleophile that has been used in the copper catalyzed allylic substitution reaction. And common allylic electrophiles include allylic halides, acetates, carbonates, phosphates and tosylates. Copper catalyzed allylic substitution typically occurs to form products from the addition of the nucleophile at position gamma to the leaving group. So, this is actually Y means here this is gamma to the leaving group. The tendency for copper catalyzed allylic substitution to form products from gamma substitution versus alpha substitution depends on a number of reaction parameters, including the identity of the allylic electrophile, the reaction solvent, the reaction temperature and the source for the organometallic nucleophile. So, this is very important, the gamma and alpha substitution is possible. Like here, this is the allylic system and Lg is the leaving group here, Lg is Cl, Br, OCr, OPOR to OSO2r and R2M, this is hard. So, this is hard nucleophile, R2 is alkyl, aryl, vinyl or aryl and M is equal to zinc. So, these are all metals. M is zinc, magnesium, aluminum, lithium etc. And this is the gamma substitution. So, alpha beta gamma substitution here and this is the alpha substitution. Alpha substitution means the same carbon where the leaving group was attached. So, that is called alpha substitution. And the mechanism. So, first we will discuss the mechanism, what happened here. If you have a leaving group, then the cuprate, first the coordination happens, earlier we have seen. Now, the oxidative addition will take place at the gamma position and the double bond will migrate. After reductive elimination and minus CUX, you get this gamma substitution product with a terminal olefin. So, here the olefin is terminal. On the other hand, X is equal to alkyl, then this kind of allylic system will form. So, here X is equal to Cn or Cl, then the gamma substitution and here the X is equal to alkyl, then this will form, that is the alpha substitution. So, here this addition is taking place at the alpha place and reductive elimination with minus CUX you get this alpha substituted product. So, why with when X is equal to Cn or Cl, you get the gamma substitute that will see the energy barrier. So, first this coordination plus 9.7 kilocalorie per mole, and here you see plus 21.7 kilocalorie per mole to get the allylic system, and then this is the gamma reaction, it is favored. And on the other hand, with this same system for the alpha cases, this energy is little lower, but the second one is higher, 24.9 kilocalorie. So, here methyl is this side and here methyl was the other side, and after that you get the alpha substituted product, and this is disfavored. So, this is favored, less energy required. So, energetically favorable this gamma substitution when X is equal to Cn. Here you can see the details. Now, we will see example. So, the reaction of the monoalkyl cuprate MECU-CnLi with a substituted cyclohexanyl acetate is regioselectivity for the addition to the gamma position. So, that we have seen when X is equal to Cn, then you get the gamma attack and occurs with anti-stereoselectivity. The corresponding reaction of the dialkyl cuprate Me2CuLi also occurs with anti-stereochemistry, but it gives a mixture of regioisomeric products. Thus, copper catalyzed allylic substitutions are often conducted under conditions that prevent the formation of symmetrical dialkyl cuprates. So, here if you see, this is a chiral allylic acetate, also there is a methyl group there, that is also chiral, and when you add MECU-CnLi, what happens? You get the gamma attack. So, this is the gamma attack, this is gamma attack product, and this is alpha attack, and both cases the stereochemistry is opposite of the methyl group, existing methyl group. However, in the case of Me2CuLi, you do not get the selectivity. So, mixtures of alpha and gamma. So, that is the importance of cyano. In the cyano case, you selectively get the gamma product, but in the case of Me2CuLi, you get a mixture. Now, we will see asymmetric version, copper catalyzed asymmetric allylic alkylation, that is also possible with suitable ligand. So, this is the allylic acetate, and this is Grignard, and here this is the copper sulfide Ar. So, sulfur is there, also amine is there, that is binding with copper, and with E2O, ether 0 degree centigrade, you get 100:0 gamma:0 alpha selectivity. So, here also terminal olefin is forming, and you get this selectivity is very high, 100%. However, the enantiomer selectivity is 42%. So, enantiomer selectivity less, because if you see the ligand, there is only a methyl group. So, if you pull bulky ligand, then the enantiomer selectivity can be much higher. This was published in Tetrahedron 2006. Now, we will see different coupling reactions. So, first we will discuss Cadiot-Chodgievsky coupling, because we have discussed the copper, it can add to aryl, even the triple bond halide, and it can give the product, alkylated or arylated product. So, the Cadiot-Chodgievsky coupling in organic chemistry is a coupling reaction between a terminal alkyne and a haloalkyne catalyzed by a copper 1 salt such as copper 1 bromide and an amine base. The reaction product is 1,3-diene or dialkyne. So, this is the reaction. So, you have to use an alkyne, and this is actually terminal alkyne. So, the reaction will happen, and this is the bromoalkyne, and copper 1 and a base. So, this is base, and then you get a product. So, this coupling happened here, CC coupling, and this is dialkyne. So, this is very important, just simple copper and base, it can give the coupling product. So, what could be the mechanism? Now, the reaction mechanism involves deprotonation by a base of the terminal alkyne proton followed by formation of a copper 1 acetylide. A cycle of oxidative addition and reductive elimination on the copper center then creates a new carbon-carbon bond. So, this is the reaction. First terminal alkyne that is acidic, this is acidic. So, this can be deprotonated by base to generate the anion, and that can react with copper to generate the copper acetylide. So, this we have seen in the Sonogo-Shida reaction also, copper acetylide, and now this copper acetylide will add to the bromoalkyne, and this will be the oxidative addition. So, this you see oxidative addition happens here, and after reductive elimination, so copper X will be eliminated, and reductive elimination you get this product. So, this is the product. So, the importance is the copper acetylide is formed, then the oxidative addition happens, and after the reductive elimination give you the coupling product. We will see some examples now. So, this is the R can be aryl or alkyl, and this is the bromoalkyne with 0.1 equivalent copper 1, that is copper iodide, and you need another phosphine, orthotoluene phosphine. This is the base, 2 equivalent potassium carbonate ethanol, 100 degree centigrade you get this dialkyne product in good yields. This was published in Synthesis 2011. Also, if you see, this is the vinyl dibromide. So, vinyl dibromide, and in situ you can generate the bromoalkyne, just treatment with LHMDS. So, lithium hexamethyl disilogen, this is called lithium HMDS, and with THF solvent minus 78 to 0 degree centigrade 1.5 hours you get this bromoalkyne, which in situ reacted with terminal alkyne with 0.4 to 0.5 equivalent copper 1, and this is the additive 20 equivalent butylamine, and this is the base 0.6 to 0.75 equivalent ammonium hydroxide, and you get this product, and the scope is broad. R can be methyl ethyl, R dash can be aryl alkyl, and this was published in recently Organic Letters 2018. Also, silyl alkyne can be also used, because the silyl group later you can use for further reaction, and with bromoalkyne, with copper 1, ammonium hydroxide, this is catalytic amount, the base, and this 30% butylamine in water, you get this coupling product in room temperature only. This was published in JOC 2002. This is another reaction. This is, you can see aromatic system is there, and the silyl group is present here with 1 equivalent butyl lithium, that is the base here, and then 1 equivalent copper 1, copper chloride here, and this is a dialkyne. So, SiMe3 is one side and Br one side. So, Br side will react and the SiMe3 will stay intact, and you can see this is actually trialkyne, and this is 52% isolated yield. This was published in Chemistry European Journal 2002. Now, we will see glacier, that is another oxidative coupling. The glacier coupling is a type of coupling reaction. It is by far the oldest acetylenic coupling, and is based on the cuprous salt like copper 1 chloride or copper 1 bromide, and additional oxidant like oxygen. The base in its original scope is ammonia. The solvent is water or alcohol. The reaction was first reported by Carl Andreas Glaser in 1869. So, that is why it is called glacier coupling. Here the oxygen is actually the oxidant. So, what you have to do, this 2 equivalent of terminal alkyne with copper chloride and base, you get the copper acetylide, and with oxygen ammonium hydroxide ethanol you get the coupling. So, this is the coupling product. And now, there are some modification, Eglinton reaction. In the related Eglinton reaction, 2 terminal alkynes are coupled directly by copper to salt, such as cupric acetate. So, here no oxygen, because copper 2 is used. Like here you need a base, of course pyridine, and copper 2 you can get this coupling product. The Eglinton reaction has been used to synthesize a number of fungal antibiotics and important for carbon-carbon bond formation via the oxidative coupling of alkynes. So, here the mechanism, the alkyne first react with pyridine, gave the acetylide, acetylide generate react with copper 1. So, this copper 1 is generated from copper 2 actually, so that we will see, and then the copper acetylide is formed, and this copper acetylide when react with copper 2 it generates a radical. So, this is very important, radical is formed and 2 equivalent of copper acetate. So, this copper acetate is reacting here actually, and then this 2 radical a dimerization happens. So, dimerization of radical, 2 radical makes a carbon-carbon bond and you get this dialkyne. Hay coupling also there is a modification. Hay coupling, the related Hay coupling has several advantages as compared with the glacier coupling. The copper TMEDA complex used is soluble in a wide range of solvents, so that the reaction is more versatile. So, here TMEDA is used in the Hay coupling. So, this is the reaction, copper 1 TMEDA, catalytic amount and oxygen, you get the coupling product. So, this is the coupling product. Examples. So, this is terminal alkyne, this is another alkyne 5 equivalent, 0.1 equivalent of copper acetate, this is copper 1, piperidine, AR. So, this is glacier coupling. Glacier coupling with base and 0 degree centigrade 3 to 10 hours you get this dialkyne, and R can be aryl alkyl and R dash can be PHCH2OH CME2OH. This was published in Synthesis. So, you can see this is a dialkyne and this reaction is intramolecular, and if this substrate is treated with 0.2 equivalent copper chloride, 0.25 equivalent nickel nitrate, 6H2, this is additional catalyst, 3 equivalent of triethylamine, 5 equivalent of pyridine, PEG 400, methanol 1:1, 60 degree centigrade, and 1 to 2 days you get this cyclic molecule. And this is actually Earlington coupling, and Y can be CO2 or CCO2 whole 2, and generally M plus N should be greater than 6. So, the cyclization will happen efficiently. So, this is macrocyclization, and for CO2 the product will be like this. So, one oxygen like this, and then you have the carbon chain, and this side also the carbon chain will be there like this. And for CCO2 whole 2 also it can be like this, CCO2 ET, CO2 ET, and you have the alkyne. So, here more carbon atoms are there like this, and this was published in JACS 2011, page number is 19976. Also, you can see this is trialkyne, and this is called Hay coupling. This trialkyne, where R3ASI can be TBDMS, when treated with 42 equivalent of copper chloride, 14 equivalent of TMEDA, oxygen 1 atmosphere, acetone solvent 20 degree centigrade, then you get this dimerized product obtained in 94% yield. So, this is actually hexaalkyne. So, this is very important that a monomer converted to dimer just treated with copper chloride, TMEDA and oxygen atmosphere. And this work was published in Chemistry European Journal 2002. So, these are very useful methods, this glacier coupling, Earlington modification and the Hay modification, they give the dialkyne or trialkynes, and this was published in Chemistry European Journal 2002. Now we will discuss Ullmann reaction. In the Ullmann reaction, biaryls are synthesized. The coupling of aryl halides to afford biaryls using copper source is called Ullmann reaction. The order of reactivity of aryl halides follows the order aryl iodide, aryl bromide, then aryl chloride. An aromatic ring having electron withdrawing groups at ortho position activate the ring toward coupling reaction. Unsymmetrical biaryls can be prepared by taking two different aryl halides. The byproducts can be minimized when one aryl halide is very reactive and the other is relatively unreactive. The reaction takes place via oxidative addition followed by reactive elimination. So, this is an important, this is actually, you can see this is very reactive. So, this is very reactive, this one, 4 nitro group, 3 nitro groups are present here, and this is the iodobenzene. Now, with copper 200 degrees centigrade you can use this cross coupling. So, this is cross coupled biaryl synthesis. Now, what could be the mechanism? So, mechanism that aryl iodide just copper, with just copper heat oxidative addition will take place and you get this species ArCuI, and now copper again will react with this system to generate copper iodide and ArCu, that is the active intermediate will form. So, this is active intermediate. Now, the oxidative addition will take place to get this species that we have seen earlier also, like two aryl groups are connected to copper. Now, the reactive elimination will happen and elimination of copper 1 iodide you get this biaryl product. So, we will see some examples now, like here this heterocyclic iodo compound when treated with copper, potassium cyanide, ammonia heating condition you get this dimerized product in 90% yield. This was published in JOC 2002. Also, if you see this nitro 2 methoxy group are present in the aryl group and with copper itself DMF solvent. So, this is very simple condition, you get 51% yield of this product, biaryl product. This was published in Organic Letters 2003, and this is an little bit complex structure. You can see here a motif is present, here many methoxy group is present, but so this is quite bulky here, but with copper 0 pyridine you can get this coupling product. So, this is very interesting, this product is forming 81% yield because the both ortho is occupied. So, both ortho positions are occupied. That means, this iodide is in the sterically hindered position, but still the reaction happens with copper. So, this is very interesting. This was published in Tetrahedron Letter 1996. Some more examples, the coupling of aryl halides with phenols using copper source known as Ullmann ether synthesis provides effective protocol for diaryl ether synthesis. Both symmetrical and unsymmetrical ethers can be synthesized, like here phenol. So, this is phenol and aryl iodide with copper base heat you get the aryl ether. So, this is aryl ether formation. Catalytic version of the reaction has been recently developed with copper 1 salts. The proposed mechanism involves oxidative addition followed by reactive elimination, like this ArOH base and with copper. So, this copper alkoxide is formed and now oxidative addition will take place. The copper, this aryl group is coming to copper and now the reactive elimination. So, this group and this group eliminates, you get this product and the copper X is formed again. So, some examples we will see. Suppose if you treat this phenol with diiodobenzene, 1,4-diiodobenzene with copper iodide, cesium carbonate, NN dimethyl glycine, then you can get this product diaryl ether. Two ethers are there in 95% yield. This was published in Organic Letters. Also, this iodo substituted benzene with this alcohol, long chain alcohol, this ether can be formed in 81% yield. This was published in Organic Letters also. Even amination is possible. So, we have seen the ether formation, now amination is also possible. Ullmann showed the CN cross coupling of anililes with aryl halides using copper source at elevated temperature. Aryl halides having electron withdrawing groups show more reactivity with aryl amines substituted with electron donating groups Catalytic version of the reaction has been developed during the recent years using copper 1 complex as a catalyst. The nature of the ligand plays a crucial role in the catalysis. So, here you can see the amino acid actually. So, beta amino acid, and this is the chloronitrobenzene with copper base, you get this CN coupling product. Now, we will discuss Goldberg reaction. So, the CN cross coupling of amides with aryl halides using copper source is called Goldberg reaction. So, coupling of amides with aryl halides. The reaction becomes catalytic when we carry out in the presence of base. The traditional method involves elevated temperature. However, the recent methods are effective at moderate temperature when copper 1 complexes are used as catalyst. So, this is the amide generally, amide, and this is the aryl halide and copper 1 base, you get this coupling product. A traditional Goldberg reaction is illustrated by the synthesis of phenamic acid and intermediate in the preparation of acridone. So, this is an example, this is simple amine here also. So, both amine and amide can be used, and this is the chlorobenzoic acid with copper oxide, potassium carbonate, reflux 2 hours, you get this product in 82% yield. So, amide or amine. Aryl iodides are favored arylating agents, and this reaction proceeds well with an electron rich aryl iodide. It is valuable alternative to the Backwell-Hartwig amination reaction, which gives base yield with electron poor aryl halides. So, this is an alternative of Backwell-Hartwig amination reaction. So, the iodobenzene reacts with copper iodide to get this one, the oxidative addition, and now this amide here, it is deprotonated by base to generate the anion, and that adds to copper. Now, the reductive elimination happens and you get the CN. So, CN coupling happened here and you get copper iodide back. So, example with amide. So, this is an example with amide. Earlier we have seen example with amine. So, here the amide is present and the bromobenzene with copper iodide, potassium carbonate microwave condition, you get this CN coupling product. This was published in Tetragon letters. And last reaction we will discuss this Castro-Stephens coupling. The Castro-Stephens coupling is a cross coupling reaction between a copper 1 acetylide and an aryl halide in pyridine, forming a disubstituted alkyne and copper halide. So, this is the copper acetylide, and Rx, X can be I, B or Cl, R should be aryl, and with base you get this cross coupling product. The reaction has similarities with the much older Rosenberg von Braun synthesis between aryl halides and copper 1 cyanide, and was itself modified in 1975 with as the Sonogosira coupling by adding a palladium catalyst and preparing the organocopper compound in situ, allowing copper to be used in catalytically. So, this was an old reaction, the modified is the Sonogosira coupling. So, when alkyne is treated with copper, then the coordination happens and the base, of course, then the copper acetylide form, and then the ARX, the oxidative addition. So, this is oxidative addition and this is reductive elimination happens and you get the cross coupling product. So, some examples now, like here a simple copper acetylide you can prepare and then you can react with iodobenzene. With pyridine reflux, you get this product in 87%. This was published in JOC 1963. Unlike the Sonogosira coupling, the Castro-Stephens coupling can produce heterocyclic compounds when a nucleophilic group is ortho to the aryl halide, although this typically requires use of DMF as solvent. So, cyclization reaction also is possible. So, here the Castro-Stephens coupling followed by cyclization. So, here this coupling first happens here and then the acid group is making a cycle. So, this is 6-membered cycle is formed, that is very favorable. 6-membered cyclic system is forming with DMF reflux 4 days. This was published in JOC 1980. Now, we will discuss some more examples of Castro-Stephens coupling. So, like this iodide having a nitro and methoxy group, when treated with copper acetylide in presence of pyridine, you get this cross coupled product, and it was obtained in 93% yield. This work was published in Tetragon Letters 1978. Also, if you see this one, this is intramolecular, because both vinyl iodide and alkyne are in the same molecule, and when this was treated with copper iodide, triphenyl phosphine, which is ligand, and potassium carbonate base, then you get this coupling product, and here the olefin geometry is retained, here was trans, here also is trans, and this macrocyclic product is obtained in 37% yield. So, this is a very important reaction, and this was published in Organic Letters 2001, page number is 3487. So, today we have discussed the copper 1 reagent. So, first we have discussed the Gilman reagent. Gilman reagent is R2CuLi or R2CuMgX, that has been used in many reactions like conjugate addition, also tandem 1 for addition, enolate trapping reaction. We have seen that the C trapping and O trapping you can do, and the C trapping case you get the trans product mainly. Then reaction with acid chloride, we have seen that the acid chloride, actually this is a very important reaction, you can get the ketones, and ketone does not further react. So, this kind of reaction is not possible with Grignard, because in the case of Grignard the ketone will further react. Reactions with aldehydes and ketones also you have seen, and in this case aldehyde ketones we have seen the trimethylsilane or silyl chloride or BF3 etherate and manganese chloride, they can be used for the higher yield. Then the reaction with epoxide we have seen, and epoxide case we have seen the Lipschutz reagent is very useful reagent, you can get higher yield. And higher order mixed cuprates we have seen that the substitution reaction also is better with the Lipschutz reagent. Then we have seen copper catalyzed allylic substitution. In this case we have seen that if CuCN is there, then you can get the gamma substitution. On the other hand, it is that CuMe, then you can get the alpha substitution. Then we have seen the Cadmio-Choudhury coupling. This is the copper 1 base, and with bromoalkyne you can get the dialkyne. Then we have seen the Glaser oxidative coupling. Here the dialkynes also is formed, but with oxygen. Here simple dialkynes can be used and simple copper 1 and oxygen. Then also we have seen the some variation, we have seen Ellington and Hay. Then we have seen the Ullmann reaction, this is very important for biaryl synthesis. And in Goldberg reaction we have seen amine and amide coupling with copper 1, and lastly we have seen the Castro-Stephens coupling, that is alternative Sonogoshira coupling. Here also an aryl halide and alkyne can be coupled with copper 1 and a base. Thank you.